All right, everyone. So this is our video on analog signals. So we're going to talk about analog signals and analog to digital converters and how your Arduino can read something that is not like a 1 or a 0, but turn it into kind of a set of 1s and 0s, and how it can get this value that's kind of some infinitely dividable value and turn it into something that we can actually quantify and make a number out of. So that's what an analog signal is. First, to understand how analog signals are different, let's review digital signals. So with a digital signal, we have 0 to 5 volts. For this entire video, you should understand that we are working in the 0 to 5 volts range. So our analog to digital converter reads on a scale of 0 to 5 volts. Digital signals read on a scale of 0 to 5 volts, and that's just with Arduinos. Now, different microcontrollers might have something different, but with Arduinos, we're going from 0 to 5 volts, and that's our range of values. So, digital signals, before we get into analog. Let's look at this little white line here. We can pretend like this white line is our voltage value. So, if we are reading a voltage value that is somewhere up here in this little box here of our 5 volt range, and I believe this is 3 volts right here. So anywhere between 3 volts and 5 volts, it's going to read a high signal. So if we're tracking this on our digital input, and what is a digital input in terms of like, is this going to be a high signal or a low signal? Well, as long as we're between 3 volts and 5 volts, somewhere in here, you can see down here, it's going to say, yep, that's a high signal. We're within this range, we know it's a high signal. And we can go to the other end here. We can look at this area here, and I believe this is 1.5 volts, so 1.5 volts to 0 volts. If we are within this range, 0 to 1.5, it's going to read that and say, okay, that is a low signal. So that is right here. You can see that is a low signal. We're going to read that as low. And it's going to say, yep, it's within this range, 0 to 1.5 volts. We're going to say that's low. But we have this weird intermediate value here, which is our high Z, and that is this kind of section where it's kind of unknown. The computer doesn't really know, like, well, is this a high voltage? Is it a low voltage? It has to figure it out, and it has to give you a number of a 1 or a 0 and say it's high or it's low, but we have no idea what it's going to spit out here. It totally depends on a bunch of different factors. So that's why we have this unknown region. And that's why we need pull up or pull down resistors in our buttons, because when it's out like this, and we're in this weird middle zone there, it doesn't know whether to say the button's pressed or the button's not pressed. So that's your digital signal. It's either high or it's low, and if it's within a certain range of values, it's going to say that it's high. If it's within another range of values, it's going to say that it's low. And of course, we have this kind of third area here where it's kind of indeterminate, and it's going to pick high or low, but we don't know which one. The point is, digital is either on or off, yes or no, high or low. Analog is different. So analog is where we get into reading a big range of other values. So if we look at this first graph here and we say that white line is voltage, now we don't have any more unknown zones here between 0 and 5 volts. We can read all of it. And so we can tell you, yes, this is any one of these different voltages in here. So ideally, we would see a graph like this. You can see the two graphs here, and the ideal signal, I'll tell you about this 1024 and the 0 here in just a second. You can see that white line is our ideal signal given our voltage. So these are kind of what it would look like when we get an analog reading versus our voltage on that pin that we're taking that analog reading off of. The problem is we're dealing with an analog signal, and let's say I have a voltage of 0.1 volts. So 0.1 volts. Well, can we go smaller than that? Yeah, of course we can. So we can go 0.01 volts. Can we go smaller than that? 0.001 volts. The point is, we can keep going down forever. There are an infinite level of voltages that we can try to read here. But we don't have that kind of processing power, and an infinite level of voltages would take an infinite amount of storage for us to calculate and quantify. So we need some way to store those values, and we have something called an ADC, or an analog to digital converter, and we'll talk about that. That is what our actual signal, I do that every time. That's what our actual signal is. So you can see on this little actual signal section here, we have all these little steps. And so those steps are kind of quantifying our signal in a set of layers. And it turns out for our certain board here, we have 1,024 of those layers. And that is because we have something called an ADC, which has a resolution. Our ADC is an analog to digital converter. Let's talk about analog to digital converters for a second. What is an analog to digital converter? Well, simply, an analog to digital converter is a component that takes some range of values that could be an infinite range of values. So maybe like a distance sensor. I'm measuring a distance from me to the wall in front of me. Well, I can measure that in meters, or I can measure it in centimeters, or centimeters can be divided down into millimeters or decimeters, or like smaller and smaller and smaller, but I need some way to quantify that in a very set value. So we take some range of values that could be infinite, and we're going to split that into chunks where it says, okay, over this chunk, I'm going to read this value. And then if I hit one more of those chunks, I'm going to increase that value by 1. So our analog to digital converter has 1,024 levels of accuracy that we can get to. And that's because it has a 10-bit analog to digital converter. So our Arduino has a 10-bit converter, which means it has 10 bits of memory. And a bit is just a 1 or a 0, right? So we have, if we have a little box here, and we have a 1 or a 0, 1 or a 0, we have 10 of these little sets here. So what is this? 4, 8. So that's 10. This is how much memory we have here. And if this is confusing, it's all right. You can kind of skip over this part. But the important thing to know is if we have 10 different sets here, so each of these is an option, a 1 or a 0. Well, there's 2 options, and there's 10 boxes, I believe. Yep, so 10 boxes there, 2 options. So that is 2 to the 10th. I will tell you that 2 to the 10th is equal to 1,024. 1,024 values that we can possibly get out of this. This is all about binary here, and reading binary is a whole different thing, but you should know that there are 2 options for each step, and there are 10 steps. So that means that we have a total of 1,024 different settings that this memory can hold. And that means that we have 1,024 steps of 0 to 5 volts that we can measure off of any given sensor. So if we wanted to look at how big each of those steps are, well, it's pretty easy. We know we have 1,024 of those steps, and our range goes from 0 to 5 volts. For full steps for 5 volts is 1,024, and for 0 is 0 volts. So if we just take 5 volts over our 1,024 steps, that says that each step, every time we go up 1 step or down 1 step, we are changing by, and I did this math earlier, 0.00488. It kind of goes on a little bit for that, volts. So each step is this many volts. So each chunk is that change in voltage, which, unless you are measuring something really, really specific, this is going to be plenty of resolution here. If we're measuring in basically 5,000ths of a volt, it's going to be plenty for our purposes. So these can't be infinitely accurate, right? we could change this from a 10-bit analog to digital converter to like a 24-bit analog to digital converter or something like that. And then we're going to get a lot more steps, and our steps are going to go down in size because maybe for every, I don't know, a millionth of a volt that we change, then we get one more step or change a step. Really don't need that kind of resolution here. But this is our analog to digital converter resolution. It's actually, this is our 10-bit resolution. So that means when we're reading in any given value, if you read it into the Arduino is going to read it as something between 0 and 1023. You may ask, well, why 1023? You just said 1024. Yes, 0 counts as one of those values. So if you have a total of 1024 values and 0 counts as one of them, then the top value is 1023, right? 1023 plus our 0 is 1024. That doesn't really make sense mathematically, but if you just count 0 as one of our values, and then there are 1023 other values, those together makes 1024. So you should know that we can read in values from 0 to 1023. All right, so after this, we will have a video on pulse width modulation, which is kind of a way to fake an output of an analog signal. And all of this stuff about resolution is going to come in handy there too. Pulse width modulation is where we can use a digital pin and send out a digital signal in such a way that it looks like an analog signal, or that it's read kind of as an analog signal. And it's very interesting, so look out for that video. If you have any questions on this, analog to digital conversion, the differences between digital and analog signals, please reach out to me. I am more than happy to go over some examples for you and to talk you through this whole process. Thanks.